Well, good morning, everyone. Congratulations on getting here for the first lecture of the final day of the conference. It's my pleasure to introduce a very, very familiar name to everybody, Mutsuo Oka from Tokyo, and he's going to talk on Milnor fibrations of mixed functions with non-isolated singularities.
Thank you very much. So first of all, I'd like to thank to the organizers of the invitation, having me this opportunity. This is my first visit to Brazil and Sao Carlos, of course. I am enjoying very much. So my talk is about mixed functions. Mixed functions, the original motivation is to study real varieties of coordination 2 and its ring structure and fibration structure. It was originally posed by Milnor's book. So we have two real analytic functions, G and H, with two n variables. X is x1 to xn, and y is y1 to yn. And so we are considering these varieties. But to study as a real algebraic variety is more complicated. So my motivation is to look it as a, a complex valued sort of complex hypersurface. But here F is defined by like this, and then you cannot avoid involving this complex conjugate of that, because you just replace X by this equation and Y this equation. So usually you have both Z and Z bar. But you can pretend it a complex variable, complex valued functions. Yeah. So the main difference with complex hypersurface is even this is on the point where this is smooth, the tangent space does not have a complex structures. Because it is defined by two functions, and so first of all, I would like to introduce this gradient vector. So gradient vector K. The K is real valued mixed function. So gradient vector with respect to the first n variables and the second n variables. So it's a vector of R to n. Certainly, this Cn and R to n are always identified by this property. So now I consider the case where K is not necessarily real valued, complex valued. Then you can consider two sorts of gradient, which is first with respect to the holomorphic differentials and complex conjugate differentials. Of course, you can write it like this. So it's complex linear combination of real gradients. But I consider it a complex vector, okay? And these two. Then, if this K is real valued, you have this obvious equality. The delta gradient and delta bar gradient is related by this. So because these notations are too long to write, abbreviate like this. Dk is gradient k, and dkx is gradient k with respect to x, and dyk is gradient y, k with respect to y. And partial k is this gradient, and the partial bar gradient k is this delta bar gradient. Okay. Okay. So the first proposition is, I think this is already mentioned in the talk of Kawashima. So we consider if a function from Cn to C. Then this point is critical point. If and only if, of course, this real part and the imaginary part is gradient is linearly. Sorry, this is dependent. Sorry. Dependent of R. Okay, and that is also equivalent with respect to this complex gradient. So this sounds a bit funny, but there exists a complex number with absolute value 1, such that this partial f is here I also omitting the bar. I need the bar here. The big bar complex conjugate of this vector is equal to this delta bar gradient times alpha. Sorry, so many mistakes. So the first point is, my idea is to use the technique of complex variable function theory. So I would like you, first of all, introduce notion of Milnor boundary, Newton boundary. So we start from Taylor expansion, like this. So nu and mu is multi-integers. And Newton polyhedron is defined by the convex hull of this point here. You see, I take sum of nu and mu plus upper half planes, where the sum is taken where the coefficient is non-zero. So if you don't have any this complex conjugate part, then this is the usual Newton boundary, Newton polygon. Yeah. And Newton boundary is defined by the compact union of compact faces of this Newton polygon. Okay. So suppose we have a face delta of a Newton boundary. Then the face function f delta is defined by this partial sum. This, the partial sum where this vector is on delta. It's face function, the lowest term with respect to this weight. And if p is a suitable weight of the variables, then of course this weight function is a linear function on Newton boundaries. So you have, because the Newton boundary is compact, it has a minimum value, and the face where the minimal value is taken is denoted by delta p. And so fp is simply f delta p in this notation. Okay. Another important concept is weighted homogeneity. But weighted homogeneity, now it split into two directions. So we have this polynomial now. Polynomial is first polar weighted homogeneous with respect to some weight p. If if p is given, we consider the S1 action like this. The row silk Z is, so this is the weight of the action, weighted action of S1. Then the value of F on this orbit is simply this times the Fz. when this equality is satisfied, we call F is polar weighted homogeneous. Of course, if this term is not, if you don't have this complex conjugate term, this is the usual weighted homogeneous polynomials. Okay? But in this case, we have another weighted homogeneity, radially weighted homogeneous with respect to Q. Q is another weight. If you, so the radial action is R plus action. R plus is group by addition or multiplication, as if you like. And so action is defined like this. Then the value of the orbit is defined is this. So for example, this phase function is by definition radially weighted homogeneous, because it obviously, you take by the phase restriction to phase. Phase has a certain weight, but this concerns with the sum. So this is radially weighted homogeneous. Okay. So F is radially polar weighted homogeneous if and only if this the sum of pi nu I. So in the case of polar homogeneity, you count the complex conjugate exponent by minus, but in the radial case, you count just plus. Okay. Okay. So of course, the mean of vibration does not exist for every mixed functions. So we need to put some conditions. For example, figure 8 not does not have any vibration on the complement, for example. So the suitable concept is non-degeneracy, which is familiar in the case of complex variables. But I put here strongly non-degenerate. So F is strongly non-degenerate if and only if for any phase delta, this function has no critical point. But you see here the torus, not Cn, be careful. Because the support of F delta is inside of the phase, so usually it can have a critical point along the axis. Okay? And yes, so here is one important remark. In the case of complex analytic functions, if you have a connected component of singular locus, then the value of F is constant, because the singular locus is the balancing locus of every partial derivatives. Okay? But in the mixed functions, the value of F need not be constant. Of course, singular locus is not the vanishing of the Jacobian, but the two Jacobian have a linear dependence. So the value can be, the value of F can be not constant. That is the main difficulty when you take care of the mixed functions. Okay, here is the basic reference. So, of course, this paper is very important. Ham and Ray. Ray is not still here, sleeping. Anyway, this paper is very important in the sense that when you have non-isolated singularities, then then you have, the small spheres and the nearby fiber. But because this has a singularity, we won't say that the nearby fiber is smooth and transverse to the sphere, but the compactness argument doesn't work because the central fiber has singularity and the transversal doesn't make any some sense, but if you have a stratification, but you cannot use usual compactness argument. And so this paper replaced the compactness argument by the sort of Thom AF conditions. Okay. And the study of mixed functions started, as far as I know, for example, the paper of Ruas and Sead Fedorowski on the very special type of mixed polynomial. It's called mixed Briscoe polynomials. And also the paper of Cisneros Molina on the joint type polar weighted polynomials. Okay. And another two papers are on mine. Basic paper is this one. I just explains the existence of minor fibrilation and so on. And this take care of the special case of polar weighted homogeneous hypersurface. Okay. They are available on the archive if you want. So first of all, we consider the convenient case. The convenient means the Newton boundary intersects to every coordinate axis. That means for every j, some monomials, mixed monomial of zj power nu and zj power mu exists in the Taylor expansion. In such a case, then combining with strongly non-degeneracy, the singularity is necessarily isolated. We don't need to assume that singularity is isolated. The assumption that the strongly non-degenerate implies isolated singularity. So the situation is much more simple. Here you have obviously transversality of nearby fiber. And in this paper, I prove that the existence of minor fibrillation in this second description of minor fiber. Also the, second description of minor fibrillation, this minor tube. And also on the complement of link. This is the original description of minor. So I call the first type description. So in this paper, I prove that both fibrillation exists and they are infinity equivalent. Okay. So in this talk, I'd like to throw away this convenient assumption. That means we take care of non-isolated singularities as well. Okay. So for non-convenient mixed functions, even the strongly non-degenerate assumption does not imply the isolatedness of singularity. But in this paper, I have proved also the existence of minor fibrillation for non-convenient mixed functions, but with some extra condition, which is called super strongly non-degenerate, which is some kind of condition on the non-compact face of the Newton boundary. Because it's not convenient, you have some non-compact face, you have to take care. But this condition is, of course, too strong. So I would like to, throw away this condition. So this is the motivation of this talk, okay? So first of all, I'd like to just formulate Rorschach-Beach inequality for this my situation. Okay, so if f is written like this, g plus ih, so real part and imaginary part, then we can consider g and h as a real analytic function of 2n variables. But of course, it's a convergent Taylor expansion, so we can consider it a holomorphic function of 2n variables. Okay? Then, obviously, by the original Rorschach-Beach inequality, you have some real number less than 1 and positive, such that this inequality are satisfied. Okay? This is the original Rorschach-Beach inequality. So now, well, this real gradient and this partial bar gradient has same norm on these two. So this inequality is replaced by like this. And so I put the theta be the max of these two exponents. Then you have this inequality. And well, this is just, I'm translating this equality in the complex gradient, like this. And so after all, we have this type of theorem. Well, for any mixed function, without any assumption of a strongly non-degenerate, for any mixed function, there is C and C prime, and this inequality is, this is just ordinary, but this, you can replace this by this or this. This is complex gradient. Rorschach-Beach, okay? So now we consider non-convenient mixed functions, strongly non-degenerate, but non-convenient. And first theorem, first observation which is important is there exists, positive number R0 and delta which is sufficient. Sufficiently smaller than the R0, such that this nearby fiber is non-singular on the ball. This sounds obvious, but this is not obvious, because as I told you, the value of f along the singular locus is not constant. So this assertion in the case of complex complex analytic function, this is obvious. But for mixed function, this is not at all obvious. Okay? So first we have to prove this. I just sketch brief proof of this. So assume that this is not true, then you use curve selection lemma. And we have some analytic path such that this value is non-zero, and the f has a mixed singularity along this curve. Okay. Then, by the previous proposition of the mixed singularity, this means we have this type of functional inequality. Here, lambda t is analytic function with complex value 1. And so let's take index I, beta j, such that zjt is not constantly 0. And then I consider this inequality in this, this is Z. this is coordinate subspace, and Fi is simply F restricted to this coordinate subspace. Okay. So this is the restriction. So for the index I in this coordinate subspace, I consider the Taylor expansion like this. Here, this first coefficient is non-zero, and this is a positive integer. And lambda t is expanded like this, and this lambda 0 is in C1, because this is complex valued 1. Okay, now we consider the weight vector A, which coming from this exponent. We gather all the exponents A1 to AM. And a complex vector B1 to Bm, which it comes from the first coefficient of this curve. Now, we have, so the partial derivatives are expanded like this. So you see the first term is the phase function of Fi by weight A, and the derivative with respect to Zj, and you evaluate at B, the vector B, and then the first exponent should be D minus Aj, and higher terms. Okay, this is just a stupid calculation, and D is this minimal value of linear function A on the Newton boundary of Fi. Then the equality it changes like this. And this says that the order of this and order of this should be same, because this is, this is order 0. The lambda t has order 0. Because the first term is non-zero complex numbers. So this turns out that the condition becomes like this. But you see, this is exactly the condition that this function from C star I to C has a critical point at B by the proportion before. But the strongly non-degeneracy just avoid such situation. Strong non-degeneracy says that you don't have such a critical point on any phase function. Okay, so this is contradiction. So this proves the smoothness of the nearby fiber. Okay, so another crucial point is to generalize Hamlet type theorem. So Hamlet type theorem is if you have a holomorphic function with isolated singularity, then there exists R0 and delta such that this V eta, this is smooth, and eta is transverse to any sphere R0 for eta is non-zero and eta is less than delta. So this is a very important lemma by Ham and Ray. And you see, this is not at all obvious because for eta equals 0, they might have very higher dimensional singularities. And they proved this using a Roger-Zevich type of inequality, and they proved that this function f and F satisfies Thomas AF condition. And that is the main point to be observed. But for the mixed function, this is not at all obvious. Okay? So that I'm going to prove. So what I do, you remember this theta? Theta is the max of theta g and theta h. And I take natural number n so that this is bigger than theta. Okay? And I consider mixed functions of one more variables. So the fz minus the u power n plus I power vn, where this new variable w is written like this, u plus iv. Okay? And I consider this hypersurface in one-dimensional higher complex space. Okay? And then I consider Whitney regular stratification of this mixed hypersurface. And in this mixed hypersurface, if you restrict to the last coordinate is 0, this is nothing but our original hypersurface. So I assume that this stratification, the restriction of to V is stratification. So the V is stratified by the some union of some stratum of this stratification. Okay. So I use this notation. G tilde is this real part of big F. And H tilde is imaginary part of this big F, okay? So what I do is first I take a positive number R0 so that any sphere of radius R less than or equal to rho 0 is intersect transversally to any stratum of the B. Okay? This is just exactly like a Hamre situation. Then the argument is almost parallel like Hamre. I just summarize. So suppose there is a point P nu converging to B such that this level hypersurface is not transversal to sphere. Okay, so first of all, I normalize the gradient vector like this, just normalization, and just consider the limit of gradient vector. And we assume that this converges to this VG and VH in a project space. Like this. Then this gradient of the one variables more actually converges to this vector. Why? This is exactly the Rorschach-Bitch inequality and the choice of this big N, the integer N. You just estimate the norm of gradient, but that argument is exactly parallel with Leham. So I don't write the more detail, but this is just easy. This norm, this normalized norm converges to this norm, and the last part is 0. This is the essential part. Now, the tangent vectors converge to tau, that was assumption. And the assumption, so this tangent space, because of the expression of the real part and the imaginary part, this tangent space is simply the real perpendicular subspace of real gradient of G tilde and H tilde. Okay? This is a real perpendicular subspace. And because we assume that this fiber here, this tangent space is not transverse to sphere. That is exactly this inclusion is, okay? Not transverse, this inclusion, okay? So if you take a limit, first of all, you get this inclusion, and then because of the previous assumption, this is in this subspace, the real perpendicular of the limit P0, and the last part is product. But on the other hand, we have assumed that this sphere is transversal to every stratum. So the limit tau should contain, so Whitney irregularity should contain this limit space, and this limit space is contained this. But because they are included here, but this, so if you forget this part, this tangent space is in this space. But this means this sphere passing through this P0 is not transverse to this stratum. This is a contradiction because we have assumed that the small sphere is transverse to every stratum. So this is contradiction, so we got a proof. Okay. So making it clear, so assume F is strong non-generate, and then the rho zero is taken as before. Then for any positive number R1, there exists positive number delta, which is depend on R1, such that this nearby fiber is non-singular in the ball. And also this level nearby fiber is transverse to sphere S of radius R, where R is in between R1 and R0. Okay, so this is what follows from the previous argument. So now we have done almost. So this is punctured disk of radius delta 0, and this is boundary of a punctured disk, the sphere of radius delta 0, and this ER delta 0 is a punctured tube neighborhood. This is the punctured tube neighborhood. So we have this map, or its restriction to the boundary, and because this map on the boundary still submersion by the transversality. So we can use standard argument by Ehresmann. This is local trivial fibrillation. So this proves that the Miller fibrillation of a second description exists. Now we come back to the first description, the original description of Miller. Okay? So we consider this map. And in this, in my paper, I have assumed that the super strong non-generality, but this assumption is only needed to prove the Hamlet type lemma. But I have proved it without assuming this. So now what I have proved here is exactly the same thing. So for sufficiently small r, mean of fibrillation of first kind exists, and it is equivalent to the second description, mean of fibrillation. Okay. So in the remaining time, I'd like to explain some applications. In my old paper, not very old, but not published yet, but it's already in the archive 3 years ago. I have given Balchenko type theorem for the zeta function of monodromy of Miller fibrillation if the Newton boundary satisfies certain strongest properties. Okay. So here is the theorem. F is non-degenerate mixed polynomial of strongly polar weighted homogeneous polynomial. So this is the additional assumption. I have explained that this phase function is always radially weighted homogeneous. But if this is also polar weighted homogeneous, I say a mixed weighted homogeneous if radially weighted homogeneous. And but in this case, the polar weight and the radial weight are usually different. So they have two different weights. But this strongly polar weighted homogeneous means this polar weight and radial weight can be same. Then I say strongly polar weighted homogeneous. So if you want to have an example, let's say F Z1. See, this is strongly polar weight homogeneous by weight 2, 1, 2, 3. But of course, polar degree and radial degree are different. So I consider the mixed hypersurface. And then in this case, I consider Newton boundaries and the dual Newton boundaries, and then I take suitable regular refinement of dual Newton diagram, and then I consider the toric modification. This involves so many things to explain, so just this is toric modification. Then if this F is a mixed polynomial of strongly polar weighted homogeneous, this strict transform is now topologically smooth. This is crucial difference comparing with a complex hypersurface. This is not smooth in general because of the mixed polynomial property, but it's topologically smooth. And data function of minifabulation can be expressed like this: the product of contribution to each coordinate subspace I. So I runs to every coordinate subspace, and the contribution of the coordinate subspace is something like this. You see, this weight P corresponds to the maximal dimensional phase of Newton boundary. And then here you have multiplicity. This is polar degree, and this is Euler characteristics. What is different from the complex analytic case? This is combinatorial, but this part, the Euler characteristic, is not combinatorial invariant. So even you fix Newton boundaries, you may have a finite number of different topologies. But anyway, the data function is written like this. So just consider one very explicit examples. Okay? So two variables. So you have two phases in the Newton boundary. So Newton boundaries looks like this. So you have two phases. But because of this factor, F is vanishing on the Z1 axis and Z2 axis. Okay? But anyway, we can apply this theorem. What is the contribution to zeta function? Zeta function can be computed considering this phase and this phase. You have two phases you have to consider, only two phases. And one phase function is this. Okay, phase function is this. And this phase function is this. Now you have to compute the Euler characteristic of each phase function. But here, this is a generalization of Ruas-Fejerovsky-Seade. If F is something like this, G nu M1 sorry, N1. So you have a mixed function of n variables and n monomials. N variables and n monomials. Then you can consider some polynomials. So this F prime is Laurent polynomial of complex variables. Now, one of the main theorem in one of my papers I listed before is the topology of inner fiber of this one and this one is exactly same. So they have the same topology. If this M1 and N1 is special, this reduced to your result. And so the contribution here is polar degree is 20, and this we have to compute this, but we use this theorem. So this inner fiber Actually, Euler number is minus 20. And so the zeta function is contribution from P is 1 minus T power 20 and 1. But you see, you have two phases, and they are symmetric by the change of ordering. So the contribution is exactly the same. So the data function is given by these simple polynomials. Okay. So I stop here. Happy birthday.
Any questions, comments?
Yeah. He's here finally. Yeah, Jian.
You use a Loyasevich inequality, but maybe what is interesting is a Loyasevich inequality for real analytic functions. And so, you know, in the case I did with Ham in the past, I used in the complex case.
Yes.
But in fact, the real Loyasevich inequality is for the real analytic case. So maybe there is a common way of thinking, but just using the real analytic case.
Yeah, actually, I use Loyasevich inequality for real analytic function G and H. For the real part and the imaginary part is the real analytic function of 2n variables, and I use Loyasevich inequality for them, and I take theta is the max of exponent. Yeah, that's right.
Thank you.
Any other question, comment?
Chairman.
Your computations reminded me of some of the things I did for looking at looking at ISIS, complete intersections, isolated singularities, and there I was using modules. And when you look at something like one vector plus equals lambda times something other, that to me just screams out modules. Have you thought about using those to try to simplify your proofs?
Yeah.
Especially the A sub F proof, that was your problem.
Yeah, exactly. In the case of complete intersection case, like the argument or the paper of Helmut Hamm, instead of one gradient, you have to consider the linear combination of several gradients. But the gradient is always complex analytic gradient. But in my case, for even one function, I have to consider two gradients. That's already complicated.
So my question is that when you prove F condition, did you use the strongly non-degenerate condition or not?
For what?
For the IF condition.
AF condition?
Have you used the strongly non-degenerate condition?
Yeah, strongly, F is strongly non-degenerate, implies the delta smaller than rho 0, such that this the nearby fiber is smooth. For eta is less than delta, and so this part I need strongly non-degeneracy. Without strongly non-degeneracy, as I told, the value of F can change along the critical point. Okay? Yeah.
At the end of your example, you showed that you could trade this mixed function for a complex analytic function.
Yeah.
Is this a general phenomenon, or is this special to this example?
This is very special. Special in the sense that your function has exactly n monomials where you are thinking of n variables. If you have more monomials, then assertion is not true. So that's why you might have several different topologies, even you fix the weight and the degree. This is very interesting.
When you created the original polynomial for a complex one, I immediately began thinking of the Lie numbers because they're going to be related to the topology of the normal fiber of your f prime.
That's right.
And I was wondering if maybe there's something else going on here.
Yeah. But the problem is here, this multi-integer can be a negative exponent sometimes. That means that this is not polynomial, but Laurent polynomial. So as long as I consider the mean fibulation in the torus, I have no problem. But in general, you cannot translate this assertion to the CN. But in the case of PPCAD or some more strong polynomials, you can do it.
Okay, perhaps we better, can we leave it at that because time's running on. So the next lecture will be in 5 minutes, but let's thank Professor Oka.